goal, we will be talking about limiting reactants and percent yield. This will be a review of the stoichiometry that we learned in goal 3, where we convert from grams to moles, moles to moles, and moles to grams. So first of all, limiting reactants. So when you in a normal chemical reaction, the reactants are always in excess. To ensure that you have products are continually being produced, especially if you're in an industry where you need to sell your product through a chemical process, you want to make sure you're always continually making product. So in your equipment, you always want to be continually supplying your reactant. If your reactant runs out, then that means that you're not going to be able to make your product. So the reactant that's in the least amount is called a limiting reactant. And sometimes you might see this described as the limiting reagent, but it just means the same thing. So how do you determine which is the least reactant? You are going to use mass to mass relationships to figure this out. You need to look at a balance equation. You will look at each of the reactants and you will solve for the product. And you'll pick the same product. Whichever reactant makes the most product is the one that is in excess. The one that makes the least amount of product will be your limiting reactant. Let's do an example. So we have our balanced equation up there at the top. So we have 3 moles of iron for every 4 moles of water, and those are my 2 reactants that can react, and I can make 2 products. I can make an iron oxide and a hydrogen gas. So the question says, how many grams of the iron oxide can be obtained by reacting 16.8 grams of iron with 10 grams of water? So what we want to do is figure out which is the limiting reactant, because that's going to tell us which the amount of product that we can make. So I'm going to solve for one of the products for from both of the reactants. So it's like you're going to do everything twice. So let's start off with our iron. So 16.8 grams of iron. And looking at my periodic table, there are 55.8 grams of iron in 1 mole of iron. The pattern is grams to moles to moles to grams. Okay, so I've already done grams to moles. My next step is to look at the balanced equation, and I'm going to go from iron to one of the products. And it doesn't matter which product you pick. I think I'm just going to do the Fe3O4 because that's the first one, but you could do the hydrogen also. So 1 mole of iron So 3 moles of iron for every 1 mole of this iron oxide. My moles cancel and my iron cancels, and so I'm left with moles of this iron oxide, and so I will just change it back to grams. And my molar mass is given to me there, 231.5 grams of that iron oxide. And so now I just need to do my math. So I will multiply and divide, and I get 23.2 grams of this product formed. So I'm going to do everything the same with the second reactant. So I'm given 10 grams as my starting point, and I will convert grams to moles, 18 grams and 1 mole. So looking at the periodic table, adding up 2 hydrogens and 1 oxygen. And next, I will do moles to moles. So looking at the balanced equation, I have 4 moles of water for every 1 mole of that iron oxide. Moles cancel, and I'm left with my moles of my product. And now, just like before, I'm going to multiply by the molar mass. And I get 32.2 grams. So from figuring out from the reactant and to the same product, I find that my limiting reactant is the first one. So notice that it's the one I have the most of, the 16.8. And so this can happen. So just because you have more of one reactant doesn't mean that that one is not going to be the limiting reactant, because there's a balanced equation that you have to figure out. So my limiting reactant is my iron. So that is my answer. So the substance that is in excess would be the water. So the iron would run out first, and I would have leftover water. All right, another thing that you can figure out with your yield of product is something called percent yield. So very rarely do 100% of the reactants turn into 100% of the products. So when we do these calculations, like I just did in the last slide, what we're finding is the theoretical yield, or the yields that we find with math. When you actually get into the laboratory, your yield should be less. And I always feel like if you can get like an 80% yield in the laboratory, then you've done a pretty good job. So you can see it's very, very rarely that's 100%. So our formula for percent yield is we take the actual yield, or that's the amount that we find in the laboratory, and we divide it by the theoretical yield, or that is the yields that we determine with math, and then we multiply by 100. So this, again, the top number is from the lab, the bottom number is just through math, and then we multiply by 100 to get the percent yield. So let's look at a sample problem. So if the theoretical yield calculated for a reaction is 14.8 grams, and the amount of product obtained is 9.25 grams, what is the percent yield? So again, it says calculated for the reaction. So that's our bottom number. Also, it's bigger. That gives a clue. And then I'll multiply by 100 and I'll get my answer. So I get 62.5%. So not great work in the laboratory if you only end up getting just over 50%. So again, I like to see them around 80%. But this is how you calculate how well your work in the lab is. Okay, let's do another example. And I'm going to use the same balanced equation just to show you that you can look at different amounts of your reactants. And again, you are going to just pick one product to find. So I could use that H2 because that is also a product, but this one specifically asks about the iron oxide. So let's go ahead and solve for this. So it says find the amount of this product formed from 30 grams of water. Divide by the molar mass. Then look at your balanced equation, and I find for every 4 moles of water, I get 1 mole of my iron oxide, or that product. And then I'm just going to multiply by the molar mass. So the amount of product I get is 96.5 grams. Let's look at our next one. So I'm starting with 40 grams of iron. Divide it by the molar mass. Again, I get this from the periodic table. On the periodic table are all the amounts that are equal to 1 mole. Then looking at my balanced equation, I find that for every 3 moles of iron, I get 1 mole of that product. So I'm using the same product I did for the other reactant. So the ending part is going to be the same, multiplying by the molar mass. And I get 55.3 grams of my product. So the limiting reactant is this one because it makes the least amount of product. So this is going to run out first before the water does. So my limiting reactant is iron. So let's find our percent yield. So this right here, this is our theoretical yield. And remember, that is the yield that we determined through math, and we just did a whole bunch of math. So this last one says if there was 43 grams of the iron oxide from this reaction, what was the percent yield? So this would be your lab number. So I would do 45 divided by that 55.3 times 100, and I get 81.4%. So pretty good results on this one. So this is a way to determine the limiting reactant by going all the way from grams to moles, moles to moles, moles to grams. It is possible to just stop when you find out how many moles of the product. But most of the time, I'm going to ask you how many grams of the product was made at some later question. So you might as well go all the way to grams when you figure this out.